Now, to get the webinar started, here is Engineering Sales Representative from Ellsworth Adhesive, Dee Gunderson. Dee?
Today's agenda includes flexible medical devices, flexible materials and assembly methods, new emerging flexible materials, assembly solutions specific to adhesives and equipment, tools and resources. Flexible medical devices. There is a multitude of flexible medical devices in our industry. We've categorized them into tube sets, catheters, respiratory items, and general devices. Within the tube set family, we include drug infusion sets, IV sets, adapters, and ports. Catheters could include balloon to multi-lumen tubing, urological catheters, and marker band bonding. Respiratory items include breathing circuits and their componentry, resuscitator bags, and oxygen masks. General devices include drug delivery devices, suture and anchor devices. Moving on, flexible materials and assembly methods.
Okay, great. We'd like to ask that you all take the time to now complete our polling question here. So our first question, what is the most common flexible substrate you use in your devices? Is it PVC? Is it silicone? Is it polyurethane, TPE, or other? So we'd now ask that you guys go ahead and put in your answers so that we have several responses in here that we can talk to. We'll give you a little bit more time here. Looks like PVC is pulling ahead, but I'll wait for you guys to all get your responses in. Okay, I'm going to go ahead and push these out. Dee, any comments on this?
I want to thank everyone for participating in the polling question. So again, it's really not a surprise to see that PVC and polyurethane lead the way. So if you looked at the previous slides, you did see, again, the common trend of those flexible medical substrates used in those devices. Thanks, Molly.
Common flexible substrates used in flexible medical devices. Silicones are generally non-reactive, stable, and resistant to extreme environments while still maintaining their useful properties. PVCs are widely produced synthetic plastic polymers used in medical device applications for over 50 years. They're light, soft, tear-resistant, and kink-resistant. They're suitable for sterilization and biocompatibility. Polyurethanes are segmented, meaning they have a soft portion that offers flexibility and a hard segment, which contributes to their high bond strength. Polyurethanes can be extruded, injection molded, and solution dipped. Natural rubber, it has a large stretch ratio and high resistance. It is extremely waterproof. Thermoplastic elastomers. These are a class of copolymers or a physical mix of polymers which consist of materials with both thermoplastic and elastomeric properties. Copolymers containing polypropylene show an increase in solvent resistance, service temperature, and processability. Common flexible substrates used in flexible medical devices. These can be subcategorized by their durometer. Basically, that is how hard or soft the substrate is. The A scale and D scale are most commonly used for measuring these types of materials. So let's focus on the 55 to 80 Shore D category as noted on your slide. Within that group, you could see flexible and rigid PVC, polypropylene, and the thermoplastics. An example of a Shore D70 material would be a tire tread. Within the Shore A family scale, a pink eraser rates at 40. Typical assembly methods for flexible materials. If we are looking at traditional bonding methods, such as room temperature cure and light cure, we see that the majority of their attributes are in the green with no issues. The bottom portion of the chart describes assembly methods that show a greater amount of issues as it relates to flexible devices.
Okay, we'll move on to the next point in the agenda, which is new and emerging flexible materials. Okay, so this slide covers a kind of an overview of some of the regulations and trends that are driving the use and change in flexible materials, specifically as they relate to medical devices. So starting with the first bullet, replacing thermoset elastomers with TPEs. And this really has to do with the fact that there are a considerable amount of leachable heavy metals that are often used in the processing of thermoset elastomers. Some examples of thermoset elastomers that had found common use in medical devices are things like SBR, latex, and polyisoprene. Going to the second bullet, replacing PVC. There's been lots of news reports over the last 5 to 10 years with regards to PVC and potential continuing health concerns related to it. I'm going to cover this in greater detail on the next slide, so for now we'll skip over that bullet. Going to the third bullet, the FDA is constantly looking at ways to reduce leachables and extractables, and specifically of late with regards to rubber and plastic packaging components. So likewise, such a regulation is really driving the need for new flexible materials that do not contribute to leachables or extractables. The next bullet, miniaturization of devices. As we look towards new non-invasive healthcare and new non-invasive medical devices, there's a constant drive towards reducing the size and invasiveness of devices. And what this does is it drives the need to replace common hardware, and by hardware I mean things like fasteners, mechanical attachment methods, which take up a lot of space, and these are now being replaced with things like flexible seals and gaskets, again, introducing new flexible materials into the market space. Co-extrusions and multi-extruded tubing, and having the ability to combine different materials, being both rigid and flexible. This is driving the need to not only introduce new flexible materials, but also introduce ways to bond these two materials together when you have multiple substrates at a single bonding site. And then lastly, heat-sensitive substrates, looking at materials that require cool assembly methods and curing processes such that they do not degrade the actual materials themselves. So let's take a little deeper look at PVC as an example. There are really 3 areas of concern when we talk about PVC. The first and probably the most commonly recognized one is the use in device concerns. There's been lots of discussions in the marketplace over the years about plasticizers and specifically about phthalates. A good example of a commonly used phthalates in PVC is DEHP. It's in there to make the material soft and flexible, but unfortunately there's a lot of health risks that have been recognized with regards to cancer, kidney, liver damage, as well as reproductive system compromises as well. The second concern, maybe not as widely recognized or known, is production concerns. There are 2 key chemicals that are byproducts as PVC is being produced and can get exposed to the plant workers as well as the surrounding environment. This is vinyl chloride monomer, VCM, as well as ethylene dichloride, EDC. And these are both considered to be potentially harmful carcinogens. And then the last area of concern, again, probably more commonly known than the previous, is disposal concerns. Both from an incineration as well as landfill perspective, there's concerns about some of the additives that are in PVC that produce a byproduct called dioxin, which is also a known carcinogen. So from the point of in use to production as well as disposal, PVC is one of the materials that probably has the most headlines in terms of a flexible material that's being looked at for change or replacement. So because of all these regulations, changes, and concern areas, there's been a lot of new materials and folks looking at ways to get rid of PVC and other materials of concern. 2 companies that are highlighted here have done just that. The first on the left side is Poly1 with their VersaFlex HC grades. They've developed these materials specifically to replace PVC tubing or other flexible tubing that has constituents of concern. You'll see here that they do reference that these materials can be sterilized by many of the common methods. They can also be easily bonded to a variety of common connectors, so things like ABS, acrylic, nylon, PC, and polypropylene. On the right side, the second example company that's listed here is a company called Techner Apex with their Metalist range. And like the Poly1, they have developed these Metalist grades, specifically their MD500 range, to be very much like PVC in terms of feel, flexibility, and densities. They likewise also cite the ability to withstand many of the common sterilization methods, including gamma. On slide 14, you'll actually see now some of the greater details of information with regards to the Poly 1 offering. So on the left side of your screen, you see the VersaFlex HC grades. In this case, Poly 1 has introduced 6 different grades. They're really split into 2 categories, the top 4 being the high clarity without plasticizer grades, and the bottom 2 being more the translucent high temperature grades. You'll see in all cases these are highly flexible, soft materials. They're all on the short A scale that Dee referenced earlier in her section on flexible materials. And they're all specifically targeted towards tubing and film applications, again, specific to the medical and biopharm industries. So Henkel Loctite actually collaborated with Poly 1 on these new materials because one of the areas of concern with any new substrates that are introduced is their ability to be assembled or bonded. So on the right side of the screen, you'll see actually some of the preliminary bonding data that was generated, and this was generated on PVC connectors. They were 1/4-inch connectors with a variety of the VersaFlex tubing, also 1/4-inch. The top table shows you the bond strengths that are achievable in terms of pull strength for a couple grades of light cure adhesives, and the bottom table shows you those same grades and the pull strengths in pounds of force with some of the cyanoacrylate grades. And really the conclusion here was that there are many PVC alternatives that are being brought to market. In the case of the VersaFlex materials, these are readily bondable based on the testing that we've done collaboratively. And for further information, there is a 2-page technical bulletin that details this testing that was done. So if you have an interest in learning a little bit more about the VersaFlex grades and the bonding studies that were done, just let me know at the end. You'll see my email address there. This is Christine, or you can put that in your review from the webinar. Okay, so we're going to move on to the next agenda item, and this is talking more specifically about some of the broader assembly solutions that are now available from an adhesive and curing equipment perspective for some of these new flexible materials.
Okay, so this is going to take us to our second polling question, which I am again going to encourage all of the attendees to complete at this time. So the question is, what is your preferred assembly method for flexible devices? Is it adhesives, solvents, ultrasonic, mechanical, or other? And we'll give you some time to get that completed. It's a quick view of preliminary results. Let's take some time to get some more in here. Okay, and I will go ahead and push out these results. Christine, if you had any comments on these?
Sure, thanks, Molly. So interestingly enough, it looks like a large portion of the audience here today, up to looks like 36% or so, are using adhesives for their flexible devices. And then really, it looks like the other methods, with the exception of ultrasonics, are sort of equally distributed, solvents, mechanical, and others. So let's dive into a little bit about several of these methods. So thank you, Molly.
So when we look at some of these common assembly methods that you folks answered the polling question on, you'll see there's really 3 of the most common ones that are used in medical device assembly. The first is solvent welding. It's an age-old technique. It still has many advantages, but there are also some considerations. In terms of advantage, it is a very low-cost solution, and it does yield very high bond strength. However, on the consideration side, a couple that I'd like to just call your attention to without going through the entire list. In many cases, the solvent welding is not compatible with unlike materials, and it is also not compatible with some of the newer flexible materials that have been introduced to the marketplace. It can also be very difficult to automate, and you have to really think about the joint design up front because it will not fill large gaps. Moving to the second type of assembly method, ultrasonics, again, a very common method used in medical device assembly. This is a method that is relatively easy to automate. It does require capital equipment. And like the solvent welding option, it does offer very high bond strengths. Again, some of the considerations or challenges, there is an investment initially in the capital equipment, as well as constant potential investment in new molds and things like that that need to be specific to the actual part geometry. Like the solvent welding, it is generally not compatible with unlike materials, and it also can be very challenging to ultrasonically weld, again, some of these newer flexible materials that have come into the widespread use within medical device assembly. And then lastly, the assembly solution method of adhesives. This is the one method that you'll see here that does have the ability to join a wide range of dissimilar materials, and those can be flexible or rigid. It does have the ability to fill large gaps, so you don't have as much concern with regards to upfront design preparation. And like ultrasonic welding, it can be relatively easy to automate. On the challenges side, there are going to be some cases that we'll talk about today that they do require equipment to cure. The good news on that is that many of the new equipment sources that are in the marketplace today are lower cost LED solutions, so we'll talk about those. The adhesives can have low peel strengths, as well as some grades can also have low temperature resistance, so just something to keep in mind if and when selecting an adhesive solution. So let's jump into some of the actual newer assembly methods for flexible materials, again, focusing specifically on adhesives. The first example we'll review is a room temperature curing adhesive. This is actually a highly flexible cyanoacrylate. You'll hear me refer to this potentially as CAs as we move forward through the presentation today, so that is an abbreviation for cyanoacrylate. This particular solution is actually new and novel. It was just introduced to the marketplace about a year ago, and it actually is different than many of the traditional cyanoacrylates that most folks are familiar with, or the superglues that people are familiar with. It is based on new novel monomers what that basically translates to is a greater enhancement in flexibility, and with that flexibility comes a higher resistance to leaks and very, very good sealing capability. With this new monomer, however, you still maintain all the outstanding cyanoacrylate properties that people choose these for, including speed of fixture, high bond strength, and substrate versatility. And the only substrate that we exclude from the bonding with cyanoacrylates is glass. Otherwise, pretty much all of the materials are viable. So this provides you with a little more detail from a technical data perspective on the highly flexible cyanoacrylate as an option for flexible material bonding. It is on the lower end of the viscosity scale, about 200 centipoise, so we'll have some running to it. It will flow and fill in gaps. It is fluorescent in the uncured and cured states. In that previous slide, you saw the glowing blue part. It does fluoresce blue. It is clear in its uncured and cured state, so there is no evidence of a bond line for transparent parts. It does, as well as traditional cyanoacrylates with exposure to gamma, ETO, and autoclave. And the asterisk on the autoclave, just a caveat there, it will not withstand hundreds and hundreds of cycles, but it will typically withstand multiple cycles. This is a new material, so the ISO 10993 certification is pending, and it has a healthy shelf life that should allow for long use. On the right side of the slide, the top chart shows you the actual shear strength of this material versus other types of cyanoacrylates. So starting on the left side of the top chart, you'll see the shear bond strength of a standard CA, and then going across to the far right side, you see the new highly flexible CA. And in pretty much all the cases, it either meets or exceeds many of the bond strengths that are achievable on things like ABS, polycarbonate, steel, and aluminum. The bottom table shows you the actual cured properties of this material, and I'll just contrast this with a traditional CA. So with this material, you actually can achieve elongations of greater than 30%. Traditional cyanoacrylates would be less than 10% typically. On the modulus scale, this material can yield about 57,000 psi in terms of modulus. Traditional cyanoacrylates would be well over 100,000 in modulus grades. And lastly, on the hardness scale, this is a unique cyanoacrylate in that it does rate on the short A scale, where most traditional cyanoacrylates do rate on the short D scale. What we're going to show you now is a video to demonstrate some of the torsional properties or the flexibility properties of this new solution.
A wide range of medical devices utilize tubing, balloons, and other flexible components as a critical part of their functional design. Common materials for these flexible components include PVC, polyurethane, silicone, and elastomers. These materials, along with new and emerging materials, can often pose challenges in assembly from both a performance and production speed perspective. Solving those challenges is Henkel's new Loctite 4902FL. Based on unique and patent-pending technology, it is a highly flexible cyanoacrylate that maintains rapid fixture speeds and high bond strengths, along with fluorescence detectable in the uncured and cured state. Here we demonstrate through an extreme torsional test the typical strength of a traditional tough cyanoacrylate. You see that due to the adhesive's rigidity in the bond line, that it fails at the tube connector interface with approximately 4 rotations. With Loctite 4902FL, after more than 30 rotations, the tube or substrate breaks, yet the adhesive bond line remains intact. Loctite 4902FL demonstrates superior flexibility and maintenance of bond strength when subject to severe torsional tests.
So what you saw in that video was that the traditional cyanoacrylate actually broke at the bond line after about 4 rotations. Compare that to the highly flexible CA that you saw towards the end of the video, that after more than 30 rotations on the lathe, it actually broke, but it actually yielded substrate failure, where the bond didn't fail, but the tube itself had actually failed. So some of the application areas that the highly flexible cyanoacrylate is targeted towards, or it's actually been either considered for use or actually already in use. The first 2 images you see are typically connectors to tubing. So this can be anything from IV to other applications where you have a tubing to a connector, but also in flexible reusable devices like you see with the stethoscope. So anywhere that you have opaque parts that need a fast fixture and highly flexible bond line, the highly flexible cyanoacrylate would be a potential solution for you. Going on to another solution for flexible bonding, this is the first of the LED solutions that I'll talk about. This is a room temperature LED curing adhesive. So this is a similar chemistry to the previous one in that it is a cyanoacrylate. However, in this case, it actually takes and combines the benefits of a traditional cyanoacrylate from a fast fixturing and curing perspective and combines it with the ability to actually cure exposed areas with light. So the image you see on the screen shows a light coming from the sort of the upper left portion shining onto the 2 black specimens that have been bonded with an adhesive, in this case the tough and light cure cyanoacrylate. The area that's outside the black lapsures, the bond line, will actually cure with the light, with the LED low intensity light. And because this is still a cyanoacrylate based on chemistry, what is confined underneath that opaque black lapsure will actually cure like a traditional cyanoacrylate. So it really offers, again, the benefits of LED curing, but also the ability to cure in what we call shadowed areas as well. So it's a very unique technology in that it offers the benefits of both. Slide 23 shows you some of the technical data or technical specs with regards to the tough and light cure cyanoacrylates. These are, for the industry, the fastest curing materials on the marketplace today, even with low intensity LED light. You can achieve tack-free curing in less than 2 seconds. We have many clients that are doing that in much less than 2 seconds. Again, they can be cured with LEDs as well as in the shadowed areas. These are a little bit higher on the SHORE-A scale versus the first solution we talked about. These are in the 70 to 80 range, where the previous was around the 60 range. Moduluses are cited here, as well as, again, fluorescence for inspection purposes. Like many of the cyanoacrylates the previous category included, these do offer excellent adhesion to plastics, elastomers, and metals. And what we've included on this slide to the bottom right is actually some bond strength data, in this case on lap shears, but involving not only traditional materials like polysulfone or PBT, but also some of the harder to bond materials. So things like acetyl, which is Delrin, some of the fluoropolymers like ETFE and PTFE, some of the polyethylenes. And you'll see that where the substrates are unprimed, the little red bars, you'll see some relatively low bond strength. When you add a cyanoacrylate primer to these and use them in conjunction with either the tough and light cure cyanoacrylates or the previous, the highly flexible, you can see your bond strength increase dramatically, especially on things like polyurethane, polypropylene, and some of the fluoropolymers. A couple of application examples. You'll notice that the difference with these is these are examples where you might have a partially exposed bond line as well as an opaque bond line. So you see the fistula on the left side of the screen as one example, and then the snap swap on the second side of the screen. Again, showing that you can bond not only hard to bond materials, like what is used in the snap swab as a polyolefin, but also the fact that you can actually cure them with light and without light simultaneously. Moving on to another LED curable adhesive. This is what we call the highly flexible light cure acrylic adhesive. You'll notice a very similar figure on the bottom that you saw previously with the toughened light cure cyanoacrylate. However, in this case, you'll see on the left side you have a transparent substrate on the top, and the adhesive is shown as being fully cured between the two parts. But on the right side, when you have that black or opaque component, this is a chemistry that does require full exposure to light. So even though you have high-powered LEDs, et cetera, if one of the components is completely light blocking, the adhesive that is in the shadow areas will not cure. The cure does not propagate. So just something to keep in mind that this particular solution for flexible materials does require full exposure to light. So some of the technical specifications on the highly flexible light cure acrylic. Again, a very low modulus on the range of about 3,600 psi. Again, very much on the short A scale, short A of 72. It is ISO 10993 compliant for medical device assembly. And again, it's really targeted for light cure applications where a high degree of flexibility or where you have different materials that have different CTEs or coefficients of thermal expansion are used. And you'll see the image on the right side shows you not only the fluorescence of the adhesive in the cured state with that little dog bone, but also, again, the extreme flexibility in terms of just that dog bone being actually bent into a 90-degree angle. Light cure adhesives, such as the highly flexible light cure acrylic, again, a wide range of use, but again, keeping in mind that the bond line must be exposed to light. So you'll see a wide range of IV components on the left-hand side, and then an endoscopic, flexible endoscope on the right side that require a very, very rapid cure, but also a high degree of flexibility. And the last adhesive solution that we'll highlight for you today are the light curable and light/moisture curable silicones. So again, another LED curable solution. In this case, there are 3 different types of these available: a low viscosity high adhesion, a medium viscosity heat and humidity resistant grade, as well as a self-leveling that does contain that secondary moisture cure. So just like we talked about with the tough flash cure products or the cyanoacrylates, this does afford both curing with light and without. So some of the technical specifications with regards to the light curable and light moisture curable silicone, really where they find particular use is high adhesion to silicone. So if there is a silicone substrate involved in terms of your flexible joint assembly, these will have the highest bond strengths to silicone. They do offer high tear strength, and you'll see from the table on the right that they're typically either clear or white in the cured state. They, like the other chemistries we talked about, or the other adhesives we talked about, these are ISO 10993 biocompatibility compliant, so they've already been screened for medical device use. And again, really where they find their use is bonding silicone components or where maximum flexibility and environmental resistance are required. So again, some of the properties are included in the table you see to the right, including temperature ranges, the shear hardness, again, very much on some of the lower short A scales, as well as a high degree of elongation ranging from 146 all the way to well above 250. I will just make a note here, and you'll see the footnote on the bottom of this slide, that although the silicones can be cured with LEDs, some of the higher powered LEDs, if there are exposed adhesive joints or there's a surface curing application, there are cases where they may require either a stronger LED or a more traditional high-intensity system in order to facilitate curing of exposed adhesive. So, as I mentioned, where the light curable and light moisture curable silicones find most application use, a lot of respiratory devices. You see a couple examples here: sleep apnea masks, traditional respiratory masks, and circuits. Again, especially where there are silicone components involved. So this table should look relatively familiar. This is the table that Dee introduced when we first started this discussion. And what we've done now is actually add to the top. We've taken out sort of those old, more traditional adhesive solutions and put in the 4 that we've just covered. And you'll notice a significant shift in terms of the no more presence of the pink or the serious to prohibitive issues with regards to these adhesive solutions. A couple instances where there are some moderate issues, specifically when it comes to curing equipment. But overall, the key areas of flexibility, ability to seal, and part design have all been pretty much addressed with the introduction of these 4 new assembly methods for flexible materials. So I'll turn it back over to Dee, and we'll talk a little bit about some of the LED curing.
Christine, thank you. So let's take a brief overview of LED curing. A light-emitting diode is a semiconductor diode that emits very specific wavelengths of light. An LED is usually a small area, less than 1 millimeter to 2 millimeter, often with optics added directly on top of the chip to shape its radiation pattern and assist in its reflection. So Most of us have seen either traffic lights or even within our own household LED systems at work. So the color of the emitted light depends on the composition and condition of the semiconducting material used and can be infrared, visible, or ultralight. This is an added benefit for the different light curing adhesives available for LED curing. LED curing and some of the benefits of LED curing. So we can look at the output of a medium pressure mercury bulb. Standard UV bulbs emit light over a wide range of wavelengths, which include shortwave, longwave, and infrared. Again, LED is a specific concentrated wavelength as noted in the chart below. So again, this helps in productivity and selection of the correct adhesive chemistry. Another key benefit of LED curing is zero infrared emission. Typically, a UV visible bulb emits high temperatures, which is detrimental to heat-sensitive components. LED systems provide a cooler cure, thus eliminating concerns about potential warping or degradation of sensitive parts. We see this often, especially with our catheter manufacturers that use very sensitive, heat-sensitive substrates. Another key benefit of LED curing is bulb life, or in this case, the LED array. So you'll see a dramatic difference in the hours of operation between an LED system and a typical bulb system, upwards of 20,000 hours in favor of LED curing. It should be noted that standard UV bulb systems must remain illuminated continually to optimize their utility, whereas the LED system is an instant on, instant off. So as you can see, within a UV bulb system, most bulbs are changed within 2,000 hours, whereas the life of an LED, once again, is upwards of 20,000 hours. LED curing and key benefits. These include lower cost used, no bulb replacement, and total lower cost overall. The one key takeaway from this slide is the bulb replacement cost. As you can see, within the first 2 to 5 years, upwards of $12,000 is expended on UV bulbs, whereas with the LED system, there are no bulb replacements. That is because LEDs use LED arrays. So examples of LED curing include a handheld unit, which is great for bench work, R&D, and small-scale assembly. This model is cordless and rechargeable. Moving on to a larger unit, this unit is higher intensity and can be mounted for potential higher productivity. The LED flood system uses multiple arrays, providing better uniformity across the curing area. Lastly is the high-intensity LED system. The flexible LED heads can be mounted and used independently of each other, making this a highly useful system, whether it is for high throughput or manual assembly.
Okay, thanks, Dee. So we'll wrap up then with a brief discussion on some of the tools and resources that are available to you as an audience. So first and foremost, we've covered a lot of ground here, and we've talked a lot about a lot of different technologies from the adhesive perspective. So I'll just call your attention to the website that's referenced on this slide. From this website, you can actually download and access a variety of different application-specific guides, as well as the guide you see on the left here, which is the full list of Henkel Loctite adhesive grades that are specifically designed for medical device assembly and specifically meet the ISO 10993 biocompatibility standard. In addition, on that same website, you can actually download any and all of the ISO 10993 biocompatibility certs. The example of one is shown there. All of our medical device adhesive grades are tested through an outside laboratory. You see here this one was done by Toxicon, but those are all available on the website and downloadable, so that at least you have some confidence that you will actually have going into your device assembly and submission that there's already some pre-testing done for you. There's also a range of material design guides available to you through the Henkel website as well. Shown here are the 3 substrate-specific ones, the red one being plastics, the yellow one being elastomers, and the blue one being metals. These, again, are all available on the Henkel website, and if we go to the next slide, you'll actually see an example of some of the contents of these. So within the plastics bonding guide, as an example, there are 30-plus different plastics reviewed within this design guide. And for each of those 30 plastics, you have basically 2 pages. The middle image that you see here is the first page within each chapter, and that really provides you with the background on the plastic itself. So the one shown here is polyvinyl chloride, or PVC. Gives you a lot of the different trade names that PVC can go by, as well as some very good technical background on the material substrate itself. On the right side of the screen, you'll actually see the bonding data. So each chapter for each of these plastics also includes detailed bonding data. And in this case, we not only took sort of the standard virgin or resin, being PVC, but we also looked at it from a variety of different perspectives, looking at different treatments of the plastic, different additives to the plastic, and then tested it with a wide range of adhesives to give you an idea of how bondable that material is over a wide range of adhesives. So again, this is a resource that is available to you for both plastics, as you see here with the red guide, elastomers, as you saw on the previous screen, as well as metals. Dee did a great job of reviewing some of the LED options. So on the equipment.loctite.com site, you also have access to a wide variety of technical solutions, not only commercial, but also a lot of the technical information that you might need to make a decision. These include the different options that are available for the Henkel Loctite equipment, manuals, rental of the equipment, as well as purchase of the equipment. So again, any questions on the equipment, you can really find a wealth of information at the equipment.loctite.com site.
Thank you, Christine. So in addition to tools and resources and the technical support, this also can be found on the Ellsworth website under Ask the Glue Doctor. We encourage you to visit that site. There you can engage our technical experts with your adhesive questions and receive prompt and concise answers. Please note the address on the bottom of the screen. Okay, so folks, please contact us. If you have any questions, we encourage you to contact Christine or I. Our information is on this slide that's in front of you. And again, thanks so much for your time and your attention. Christine?
Thank you again, and I think we're going to open it up to some questions that have been submitted, so we'll turn it back over to Molly.
Okay. We do have about 20 minutes for questions, so as a reminder to any attendees out there, if you have questions, please make sure that you get them submitted now so that we can make sure to get your questions addressed. So our first question here, and this one's going to go to Christine. What are you seeing as flexible materials most at risk from a regulation perspective?
Okay, Molly, thanks for that question from the audience. So looking back to some of the earlier slides that Dee covered, probably the material that we see most or we get questioned most about in terms from a bondability perspective specifically is PVC for sure. And I think that was one of the materials that in our polling question most people were citing as one of the materials they use the most. I think because of the publicity and the many issues that are going on, as you saw with, production of the PVC, use of the PVC, and then disposal, that's clearly one of the key ones that are an issue. And we do see some of the thermoset rubbers as well, probably not as much of late, but in past history we have seen things like latex and polyisoprene as well. So those would be the materials that from a bonding perspective and a regulation perspective we get most asked about.
Okay, great. And Dee, this next question is for you. How do adhesives perform with materials that contain high levels of plasticizers?
Oh, thanks, Molly. Yeah, plasticizers are often used in, for example, PVC tubing that we spoke about previously. And occasionally, again, depending upon the amount of plasticizer, an isopropyl alcohol wipe can remove the plasticizers on the surface. But over time, migrating plasticizers can find their way to, of all things, the adhesive, and that could compromise the bond line. So one method we often suggest to test if plasticizers are present is to prepare controlled and aged assemblies. You can expose the aged samples at 60 C for approximately 2 weeks and test the bond strength versus the control samples. So this type of conditioning will often drive plasticizers to the surface and result in a bond strength reduction. So if this is the case for you, we would suggest using a substrate with less plasticizer or one with no plasticizer at all. So I'll turn it back over to you, Molly.
Okay, great. Thanks, Dee. We're going to go back to Christine for this next question. How is the biocompatibility of adhesives tested? Is it done on actual devices?
That's a great question, and one that we actually get quite frequently. And the answer is no, we do not test typically the biocompatibility on devices, primarily because every device is different and configurations, et cetera. So a couple of key things that we do remind our clients and partners with regards to biocompatibility tests. It is the fact that the adhesive must be fully cured. So any submissions that Henkel or any adhesive supplier does to an outside lab like Toxicon or NANSA, it's really critical that the adhesive be properly and fully cured. In the case of Henkel, we sort of do what I would consider to be sort of a worst case test. In many instances, we're actually testing the bulk adhesive, and by that I mean if we can, we will actually cure a film of adhesive. So imagine a plaque of adhesive cured completely, and that is what is typically submitted for the full ISO 10993 biocompatibility. There have been some instances with certain adhesive chemistries where that cannot be easily done, having cured films made. So in that case, most of those adhesives are tested on sort of control specimens, in most cases a polycarbonate lapture that's a medical device grade that's known to not contribute to biocompatibility. So hopefully that answers that question.
Okay, great. And our next question is for Dee. How do these flexible adhesives perform following sterilization, specifically gamma? I think we may have lost Dee. Christine, is that a question that you can take?
Sure. I'm sorry, Molly. I'm back on the line. Thank you.
Okay, I'm sorry.
Sorry. So again, thanks for the question about the gamma sterilization. So just a further sterilization within the medical device industry, there are two others. One would be ethylene oxide and autoclave, just as an FYI. So gamma radiation is an acceptable method of sterilization. Oftentimes you can see bond strength slightly increased by exposure to gamma. So for example, we have seen cyanoacrylates demonstrate an increase of beyond 30% of initial strength following 50 to 100 kilogram gamma exposure. So that possibly suggests further curing of the adhesive, but we always suggest to end users to determine the effects of sterilization on their device and the cured adhesive. So thanks, Molly.
Okay. And Christine, we're going to come to you on this one. How can I best determine adhesive cure?
Okay, again, another common question we often get, especially as adhesive suppliers like Henkel and Ellsworth. In most cases, most of our clients, we suggest that, and this is what they typically do as well, is do some sort of physical test. So that physical test could be something bond strength related, it could be a hardness test, et cetera. We have had clients that do look for a bit more information, a deeper understanding of cure, and there are analytical that can be used. Things like FTIR is a method that we often house to quantify degree of cure, and really looking for conversion of double bonds to single bonds. But that's unfortunately not typically a method that can be employed online. There are some other techniques out in the marketplace in terms of some adhesive built-in monitors and things like that, but none of those have been as quantifiable and specific as a true analytical test such as IR. So again, typically the recommendation is to look towards a physical test to ensure cure, especially in a production line environment.
All right, and Dee, this one's for you. What specific wavelengths of Cure LED systems are readily available today?
Thanks, Molly. So again, these are measured in nanometers. So we're looking at 365, 375, 385, 395, and 405.
And our next question for Christine, how do these new adhesive solutions for flexible devices compare to solvent welding?
Okay, so I think we saw in the polling question that although adhesives were maybe the top method that's being used by the folks on the phone, solvent welding and some of the others were, I think, tied for second, so not uncommon to ask the question about comparison to solvent welding, which is obviously commonly used. This is one of those questions where it really does depend on the substrates you're talking about as well as the joint design. So you may recall that when we talked about the different assembly methods that, one of the key issues with solvents is its potential inability to join dissimilar materials. So clearly that would be one red flag or one issue, because you may not get adhesion to especially some of these newer flexible substrates that are being introduced. But I'll just give you sort of an example from my history. We were working with a client who was actually doing a tubing assembly. They had done it with solvents for quite a while. And because of environmental issues and some of the things we've talked about with regards to materials changing, et cetera, they actually evaluated one of the flexible solutions we reviewed today, the highly flexible CA or cyanoacrylate. And in both a large and small diameter tubing assembly that they had, we actually did demonstrate to them about 2x the bond strength of the solvent. So clearly there's going to be cases where the performance is equal between solvents and adhesives. I'm sure there's going to be cases where one may leapfrog the other slightly, but in that particular case, and it was a PVC case, the adhesive did actually significantly better than the solvent. So again, but it would depend on substrates, joint design, and certainly some other environmental factors if it was going to undergo some kind of exposure.
Okay, and this looks to be our final question, and this is going to go to Dee. How quickly does the output of a typical LED cured system decline?
Thanks, Molly. So degradation for the LED system is very slow and very gradual. So as an example, if we look at 20,000 hours, we would still expect more than 70% output to be present. So if you contrast that with your UV bulb system, which typically requires replacement 2,000 hours, it's a significant cost savings in terms of, again, replacement bulbs. Obviously with the LED array, that goes for at least 20,000 hours with that 70% output. Thanks, Molly.